Hi, everyone. My name is Guy. I'm a PhD student at Stanford. I'll be telling you about some joint work with Greg, who's a professor at Stanford, on adaptive and oblivious statistical adversaries are equivalent. The sort of problem we'll care about in this work are statistical tasks. These are settings where there's some unknown distribution D that you want to know something about. And you get access to D through a sample of points drawn IID from it. You run your algorithm on the sample S. This broad setting includes lots of things you might care about, things like supervised and unsupervised learning, parameter estimations, say you want to know the mean of this distribution, etc. Really, it's the go-to way for formalizing, I have some data, and I want to know what this data tells me. Okay, but one additional thing not captured by that very simple setting on the previous slide is a notion of robustness. That perhaps your data is not truly drawn independently from the distribution of interest. Perhaps it's been corrupted in some small amount. And there's lots of different formalizations on what it means to be robust. Perhaps the first of which, due to Huber, more than 50 years ago. In Huber's model, there was some unknown distribution D, the one you care about. But before you got to take a sample from it, an adversary corrupted it. In this model, they introduced some eta fraction from some distribution E. Essentially, they're introducing some small amount of outliers. And the corrupted distribution is a mixture between your original clean distribution and these outliers. Then you draw a sample of points from this corrupted distribution. And finally, this sample is given to your algorithm. So, this having an algorithm that works, regardless of the way the adversary corrupts it, encourages you to have some sort of outlier robust algorithm. But there's a different way we could have defined this, a slightly subtle twist, which in this adaptive variant, first we draw the sample S, then an adversary gets to look at the sample and corrupt it to a sample S hat. And then you run your algorithm on S hat. And the key distinction between this adaptive adversary, so-called sample adaptive adversary, to the oblivious one on the previous slide, is that the adversary gets to know the sample S before making the corruption. So perhaps once they know the sample, there's like certain patterns that they want to destroy that are only in this particular sample that they didn't know would be present just given the distribution D. Okay, and there are a lot of different adversaries you can define. Here are 3 standard models among many others that are well studied. On the oblivious side, you can have the additive noise where you get to add some distribution, subtractive noise where you kind of take some mass out of the distribution, or strong contamination, which is both. You can think of it as either removing some mass and then adding some new mass back in, or you can think of it as kind of just shifting mass to other portions. And for each of these, there's an adaptive variant. These are often more intuitive to define. The adaptive additive adversary gets to add points to the sample. The subtractive additive adversary gets to remove points from a sample. And in strong contamination, the adaptive variant gets to just change some fraction of the points. Okay, and there are many more than these. That some of them are, in supervised learning, for example, agnostic noise is one that's very common to study. So some of them depend on the particular setting. So the main motivating question of this work is, do we really need so many distinct models of robustness? Let me tell you a little bit about why this is an interesting question. If we can reduce the number of models, there are a few benefits. The first is an efficiency one, right? So we think about all the tasks we care about, all the different concept classes we want to learn, all the different distributions we want to learn, parameters we want to estimate, et cetera. Let's think about every different model of robustness that someone has defined. In each intersection of these, each task, which each model leads to a separate formal problem, right? It could be its own research paper, maybe a new algorithm, maybe a new analysis. Let's say so like an explosion of different things that we kind of have to study if we want to get a full understanding of what it means to be robust for these different tasks. So, this is a lot of work. It'd be more helpful if we didn't have to do quite this much. The second point I want to make is, insofar as we can think of how this translates to practice, when a practitioner wants the algorithm to be robust, they might have some intuitive notion that their data is a bit messy, but they don't, formally write down the exact adversary model that applies to their work, that applies to their setting. And what this means is, they don't really care about how many models there are. They just want one that is, some broad notion of robust. And kind of the ideal setting from the perspective of the practitioner is there's just one model of robustness, and they can just, pull algorithms from that one model when it works well. And the more there are, the more complicated this translation to practice becomes. Okay, so that motivates our main result, which I'll tell you formally what it means in the coming slides, but roughly speaking, we show that adaptive and oblivious adversaries are equivalent. So this means that you can collapse this question on how adaptive your adversary is. In each of these vertical columns, there's only one model you have to care about. And as alluded to, there are more models for what it means to be robust, and we have the similar collapse between the adaptive and oblivious variant in all of these. Okay, so in the remainder of this talk, the main thing I'm going to do is formalize this result. It's very high level right now, but there is a formal statement, and I hope you understand it by the end. The second thing is I just want to state the key lemma we have to prove, because even stating that, I think will reveal a little bit about how we prove a result like this without getting into too many details. Okay, so in order to formally state our result, I need to define a very simple algorithmic thing, something we call the subsampling filter. So the subsampling filter starts with some data set that contains some fairly large number of points, and it just draws a uniform subsample of the points. And we use sub with m to n in the subscript to denote a uniform subsample of n points drawn from a size m sample. This will be important in the next slide. Okay, so in this equivalence between adaptive and oblivious adversaries, actually one of the directions is well known and fairly easy to show, which is that adaptive adversaries can only be harder than their oblivious counterpart. Roughly speaking, the adaptive adversary only has more information. It knows the sample when choosing the corruption, so it can only be more powerful. This work is primarily about the other direction. We show that for any algorithm A and any statistical task T, just think of this as your favorite learning problem for now. I'm going to formalize what this means in the coming slides. If the original algorithm solves this task in the presence of the oblivious adversary, then a subsampled version of it solves the same task in the presence of the adaptive adversary. And this parameter of how much subsampling do you need? So m, the sample size of A prime, will be polynomially larger than the sample size of n. And we also have this dependence on the log of the domain size. The way I like to think of this is that the original algorithm, well, it takes in n samples, each of which take log domain size many bits to represent. And so A prime takes in a polynomially larger sample if we interpret it as the number of bits needed to represent the sample. Okay, there are a few remarks I want to make about this algorithm, this reduction. The first is that it maintains computational efficiency. So if A was an efficient algorithm, then A prime is as well. It just, it has to run A once, and one time it has to subsample a polynomially larger sample. So both of these are computationally efficient. And it's actually crucial that this is computationally efficient for this result to be interesting, because in many settings of robustness, if you don't care about computational efficiency, there's usually some sort of brute force approach you can do. Roughly speaking, you just guess what the correct data set is, the uncorrupted portion of it, by brute force running over all possible subsets of the data. And often, if you just kind of follow that blueprint, it's not too hard to show that you can take an algorithm that wasn't robust at all to begin with and create a robust one. But the setting becomes much more rich when you consider computationally efficient algorithms, and our reduction maintains efficiency. The second point I want to make is it's an extremely black box approach. So it applies to any algorithm A. It doesn't need to know what task you care about. You subsample it, and immediately it now is robust to an adaptive variant of whatever oblivious adversary it was robust to before. And I think this is really nice because it gives you a general purpose technique that, roughly speaking, amplifies robustness. So even if you don't know a lot about your setting, you can try subsampling and you get something a bit more robust. And the third is that this applies to all variants of oblivious and their adaptive counterpart adversaries. On the previous slide, I defined a few, but the way we prove this is we kind of define a general framework on what it means for an adaptive and oblivious adversary to be the same up to their level of adaptivity. And this result then applies to all of these adversaries. It also applies to things that are kind of halfway between oblivious and adaptive, something like malicious noise, if you know what that means. Okay, so it applies quite broadly. And I should mention some prior work. A couple years ago, this is a result of myself, Jane Lang, Ali Malik, and Liang Tan. And we kind of thoroughly studied this adaptive versus oblivious adversary question. And we showed that if the algorithm A was a statistical query algorithm, then a similar result holds. So basically by constraining the space of possible algorithms, we're able to show an equivalence within that algorithmic class. And then this work here is showing that even without a constraint on the algorithm, kind of just in general, these adversaries are equivalent. Okay, let me mention a couple of lower bounds putting this result into context. It's about kind of these two polynomial parameters. The first is there was a recent work just a couple years ago that really thoroughly investigated Gaussian mean testing for a lot of different adversary models and kind of figured out the exact sample size needed in each of them. And as a consequence of this, you can look at the sample size you need for an oblivious adversary and its adaptive variant in their paper and see that any such result must have an increase in samples, because just to solve that task requires more samples in the adaptive setting than in the oblivious adversary setting. I think this polynomial is n to the 1.5. In our work, we also show a lower bound for a different task, also showing a similar polynomial dependence. The second is this dependence on log of domain size. One way to view it is just this bit complexity of my input, but I think it's still interesting to figure out, do we need a dependence on the domain size, or can we get a cleaner, just poly n statement? And what we show is that it depends on the adversary model. We, roughly speaking, characterize whether this additional term is necessary in terms of something we call the degree of the adversary, which captures some notion of how rich the possible corruptions it can make it is. And there are some adversary models for which their richness does require this log domain size term, but others, like subtractive noise and agnostic noise, which I briefly mentioned, you can just write n equals poly n, and that will suffice. Okay. All right, so the last thing to do is to formalize this notion of a statistical task, and then this result will be fully formal. So for that, I'll need some helpful notation, which is, okay, so the oblivious adversary, remember it corrupts distributions D to distributions D hat. And I want to have some notation for the space of all possible corruptions it can make. So I'm going to use C of D to denote this space. And fix your favorite adversary model. Here, the image is strong contamination if you know what it is, but everything I say will apply quite broadly. So just kind of fix one specific oblivious adversary. It has a space of possible corruptions. Then the corresponding adaptive adversary also has a space of possible corruptions. And for every set S, I want to use C of S to denote the possible corruptions the adaptive adversary could make to this set S. And this notation now lets me define what it means to robustly solve a statistical task. So first, a statistical task is just a set which contains distributions and then the good outcomes for that distribution. Like, what would I be happy with outputting if my input was this distribution? And an example is, one simple task is I want to estimate the mean of a univariate Gaussian in one dimension. And this task is formalized by, well, all the distributions I care about are just normal with variance 1 and some unknown mean mu. And if my samples came from a distribution with mean mu, I'd be happy with any output within plus or minus epsilon of this mean mu. Okay, and then we say an algorithm solves the task T in the presence of an oblivious adversary if the following holds. So for every distribution you care about, for every oblivious corruption of that distribution is some d hat, then if you draw a sample from this d hat, you run your algorithm, you will fall into the good set for that distribution with probability 1 minus delta, very high probability. Okay, this hopefully will kind of formalize the kind of pictorial diagrams I had at the beginning of this talk on what it means to robustly solve a task. And the adaptive adversary is a similar definition. The only difference is, now the corruption happens on the sample. S hat is drawn from anything in the corrupted set, and you still have the same failure probability. Okay, so now with this notation, I can fully formalize our main result, which is, if you solve a statistical task with the oblivious adversary, the subsample of the algorithm will solve the same task. And the failure probability goes from 1 delta to 2 delta, where you have a poly 1 over delta dependence in the sample size M of the new algorithm. One thing I should mention about this failure probability is I didn't even mention it on the last slide, and that's because in most settings you can amplify this for free. For example, in learning, there are kind of simple reductions for amplifying the failure probability without any cost. So for most settings, once delta is a constant, we don't really care too much. But if you care about the dependence on delta, it's a polynomial one. Okay, so what I want to spend the last couple minutes doing is just to state the main lemma we have to prove, which is a simulation lemma. We show for any adaptive adversary, there exists an equivalent mixture of oblivious adversaries, what we're calling a randomized oblivious adversary. And I'll formally state that on the next slide, but let me just say that interestingly, if you replace the word randomized here with deterministic, it doesn't work. So if you kind of try to do like the most naive simulation approach, you can show that it's just impossible. So we need something a little bit more delicate. So what we actually show is, so you start with any base distribution D, this parameter delta, anything greater than 0, and any strategy of the adaptive adversary, right? I want to fix an adaptive adversary I care about. And what's a strategy? It's a mapping from samples S to their corruptions S hat. So these are like the adversary could choose whenever it sees S to map it to S hat. So now kind of fix that function. Once you fix that strategy, it gives you a distribution over samples you're going to see, right? So what's going to happen? First, you draw a clean sample, S from your distribution D. Then adversary, following their strategy, corrupts it to some S hat. And then before we pass it to A, remember, we're going to subsample down. So we're going to get some T, which is a random subsample of S hat. And the subsampling step is crucial to the simulation lemma, and it's also crucial to our main result holding. So what we really care about is the distribution of subsampled inputs we get from this adaptive adversary. Okay, the lemma says that there exists some mixture of oblivious adversaries. And when I say mixture, what happens? So you start with your base distribution D. Then the adversary, it doesn't deterministically corrupt it. It just draws from this mixture to decide on a corruption D hat for this original distribution D. And then you draw a sample of points from this D hat independently. And our guarantee is that the TV distance between the distributions of samples in the two settings will be delta close. So, a sample T, from this subsampled adaptive adversary will look extremely similar to the sample S from this oblivious adversary, close in TV distance. So like over like the entire sample, those two distributions look quite similar. Okay, and I won't say too much, or I really don't say much at all about how we prove this, but let me just say at a very high level that this simulation actually, like, there's an almost algorithmic description of it. We kind of described how the oblivious adversary looks at what the adaptive adversary chooses to do and builds this, distribution over possible corruptions. It's not efficient by any means, but it is human interpretable. And there is some intuition for why this particular strategy is a reasonable one for the oblivious adversary to do. Okay, so to recap, our main result was that we collapse this axis. We don't really care, like showing that you don't need to care about whether an adversary is adaptive or oblivious or anything in between. You only need to care about like the sort of corruption it makes, showing they're equivalent with this very black box reduction that doesn't need to know anything about your algorithm. I just want to close with an open question, and kind of it's like a broad area for research. But this builds into a general question of how robust is robustness. So once I have an algorithm that is robust by one definition, can I, does it mean that there's going to be a lot of other robust algorithms for the same task? And in practice, this tends to be the case. When people are able to, learn a concept class robustly by one definition, often there are others that follow with slightly different analyses or slightly different algorithms. And I think this is a very fruitful line of work. And you can ask kind of between these different models, not just moving in the adaptive oblivious direction, but between, say, additive and strong contamination, for example. How similar are those models? And when you move to like beyond just adaptive versus oblivious, I suspect you won't get quite as clean statements as we got in this talk, but I still think there could be a lot of interesting work to do there, and already I kind of seen some beginnings of it. Okay, that's what I got. Thank you for your time.